Okay. Tell me something about inverses. Do you remember anything about them? Inverse facts. Anything. Just get the conversation started. Hey, what's an inverse? Okay, so they're opposites. Okay, so they're things that undo each other, right? Like multiplying by 2 and dividing by 2, like in that equation that we just solved. Okay, so inverses undo each other. Or they cancel each other out. Okay, so that's an important inverse fact. That's how we use inverses. What about algebraically? So we can solve for an inverse algebraically. Like if I wanted to know what the inverse of a function was. Do you remember how to solve for that? I can write it with a -1, but that doesn't actually help me find the inverse.
You just switch the x and y.
Yeah. So algebraically, to find an inverse, we switch the x and the y.
Isn't it possible to find an inverse by taking all the signs like addition, subtraction, multiplication, and division, and just switching them with their opposite?
Not exactly, because the order of operations also switches. So it's a little bit more complicated than that. So when we switch the x and the y, like if you had the function y equals 3x minus 2, and you wanted to find the inverse, you would turn that into x equals 3y minus 2. Right? So you remember doing something like that last semester, and probably last year as well. So you switch the x and the y, and now you've got to solve for y. So I would add 2, but then I would have to divide by 3 to get the y by itself. So it's not quite as simple as just switching each operation individually to its inverse, because the order of those operations changes as well. Okay, so this would be the inverse. All right, so that's how we do it algebraically. What about on a graph? If I have the graph of a function, how could I graph its inverse? Ashley?
A reflection across y to x.
Yeah, on the graph, it's a reflection across, the inverse is reflected across the line y equals x. So an inverse is a reflection across that slanted line y equals x, a line with a slope of 1 and a y-intercept of 0. And what happens to the individual points? If I have some point x, y, yeah, the point on the other side, the point on the inverse is going to be yx, which again, just like we do algebraically, means we're switching the x and the y values. So the x value and the y value swap. Okay. And remember, when we're talking about functions, we usually think about the x value as the input and the y value as the output. So that's what we're going to do when we use inverses of trig functions. We're swapping the input with the output from a normal trig function. When have we used, say, the inverse sine, inverse cosine? We've used them to do some things, right? you remember? No? Okay. Well, if not, you'll remember in a minute. All right. So these are some inverse facts. Let's think about some functions and their inverses. So I'm going to write a function down here, and I want to think about what its inverse would be. So for instance, let's say I had the function f of x equals x minus 3. Any idea what its inverse would be? This one's a pretty simple one. Yeah, it'd be x plus 3. And you can solve for it algebraically, but there's only one operation happening here. It's subtraction, so the inverse is going to be to add. But if you don't believe it, you can switch the x and the y here. Remember, f of x is like your y value. So you're going to switch it and get x equals y minus 3, then solve for y, so add 3 to the other side. So the inverse function would be x plus 3. Okay, so let's think about how this switches the inverse, the input, and the output. So what if I wanted f of 10? What does that mean? Yeah, I plug 10 in for x into the function f. So that's 10 minus 3. So f of 10 is 7. Agreed? Okay. So for the inverse, I should be able to switch the input and the output. So for the inverse, I'm going to plug in a 7. So f inverse of 7. And what am I going to get out? Yeah, 7 plus 3 is 10. So that's how inverses work. You should be able to switch the input and the output from the original function. So for the original function, I plug in a 10, I get out a 7. Then for the inverse, I plug in a 7, I get out a 10. Okay, so that's how inverses work. Let's try another one. What about... What about the function 2x? So another simple one. What would the inverse function be?
X divided by 2.
Yeah, instead of multiplying by 2, I'm going to divide by 2. X divided by 2. So if I evaluate my function f at some value, f of, I don't know, 4. F of 4 is 2 times 4, that's 8. So what equivalent statement could I make about my inverse? Yeah, so I would plug in 8, f inverse of 8, so 8 divided by 2, and my output would be 4. Okay, so this is how inverses work. For the original function, you plug something in, you get something out. For the inverse, you switch those two things. Bonus question from Algebra 2. Let's see if you remember. What if my original function was, let's say, e to the x? What would my inverse function be? Better. Good guess. Yeah, it's something with logarithms. Remember logarithms and exponentials. Yeah, it's a logarithm with the base of e. It's the natural log, everybody's favorite. Algebra 2 flashback. And these will come back up in this class as well. Yep. Okay. So let's apply the same idea. Well, yeah. Let's apply the same idea to trig ratios, to trig functions. Okay. So let's say I have a function such as, I don't know, sine of x. And let's say I have an inverse function. And we're going to call the inverse function, we're going to call the inverse function just sine inverse of x. Now there's an alternate way to name this, and sometimes we'll write it like this. It's also called arc sine of x. So this is just two different ways to write the same thing. Usually for mathematicians, they'll write it like this because the negative one is kind of confusing. It makes people think about reciprocals. But remember, these are different. An inverse is different than a reciprocal. So this is another way to write the inverse of sine. It's called arc sine. Remember, an arc is like a part of a circle. And remember that sine and cosine and all these trig ratios are very closely tied to circles. Okay, so for instance, if I used my original function, I might plug in, what sort of thing do I plug into a sine function? Sine of, well, what would a question be? Hey, what sine of blank?
45.
What?
45 degrees.
45 degrees. Okay, so what sort of thing always goes in right here? 45 degrees. So a temperature?
Oh, like degree, like ratio.
Okay, so some sort of angle, right? So your angle is an input, and then your output is going to be, either some fraction if it's one of these nice pretty angles, or at least some decimal. It's going to be a ratio of some sort. So what would the sine of 45 degrees be? Yeah, square root of 2 over 2. And I'll usually refer to this as we can call it the ratio or the sine value. So some of them we can find exactly, but only if it's one of those nice pretty angles, like the multiples of 30, the multiples of 45. There are other angles that can be found exactly, but we're not going to. Like multiples of 15 you can do. Or we talked about on the test, I had you come up with a way to convert multiples of 10 using pi over 18. Maybe you remember that. I know the test was a long time ago and I haven't passed it back yet. That's my bad. I've graded the first 2 parts, and those grades are in the grade book. I did pretty well on those so far. Okay, so let's focus. So, what would an equivalent statement be? What would an equivalent statement look like using the inverse function? So what am I going to plug into my inverse function? Not an angle, but I'm going to switch these two things. I'm going to plug in a sine value or a ratio, like the square root of 2 over 2. And what sort of thing should I get out? What should my output be? Yeah, in this case, 45 degrees. So, some angle. So again, I'm switching my input and my output. That's how inverses work. So they work backwards. Okay. Now, side note, and we'll talk more about this a little bit later. So you told me that the angle that has a sine value of square root of 2 over 2 is 45 degrees. Is that the only angle that has a sine value of the square root of 2 over 2? What is there another angle? What's another angle that has the same sine value? Yeah, 135 would have the same sine value. Is that the only other angle? No. 225 would have a negative square root of 2 over 2 as a sine value. But what if I take 45 and I wrap all the way around the circle and get back to the same spot? 405 at 360. That angle would have the same sine value as well. So how do I know my answer here is supposed to be 45 and not 405 or 135?
Terribly much matters because they're coterminals. So I mean, anything you're going to do with them is going to end up with the same answer anyway.
That's true. And so what we're going to do, and we'll talk about this later, is basically choose which output we want. So do I want 45, 35, or 405? I probably want 45, right? That would be the simplest one. Well, we're always going to take it from a certain part of the unit circle. We'll talk about that in a little bit. So we're going to restrict ourselves to certain values when we're using the sign, so that we don't end up with an infinite number of answers. Okay, but there's the idea. So, quick English translation. When I see this question right here, when I have sine of 45, I'm asking myself, what is the sine value of the angle 45 degrees? And when I see the sine inverse, what I'm asking is not what is the sine value, but I'm asking what is the angle. What is the angle that has a sine of the square root of 2 over 2 in this case? So that's what this is asking right here. What angle has a sine ratio of the square root of 2 over 2? And your answer is going to be this angle. Okay, so this is how we use inverses in trigonometry. And they're going to be useful, like other inverses, for solving equations. So to help us answer more questions involving the inverse, let's sketch a quick graph. So first I'm going to graph sine of x. You've probably seen this graph before. We've drawn it every day for the last 2 or 3 weeks. So I want to make sure I label my axes. I'm going to go from 1 to -1. And I'm going to go out to 360 in this direction, out to -360 in this direction. Okay. And before I graph this, I'm also going to graph sine inverse. So I'm going to graph sine inverse on the right. Now, what is going to change between the sine graph and the sine inverse graph? There's more than one answer to that question. But the biggest thing is that for an inverse, we switch which two things? Yeah, the x and the y. So when I'm setting up my coordinates, what's going to be different? What?
Go down instead of up first, like to the right.
Wouldn't it be like a vertical?
Like a vertical wave? Yeah. So what we're doing is we're going to switch our axes. So I'm going to put my x-axis over here. But now it's going to be my y-axis. So here I had angles on the x-axis. I'm going to put my angles on the y-axis. And here I had sine values on my y-axis, my output. Here I'm going to have sine values as my x-axis, or my input. So on my x value, now I only need to go from -1 to +1, because those are my sine values. And on my y-axis, because I'm using angles, I'm going to make it go from -360, which would be down, of course, all the way up to +360. So I'm taking these coordinates, in other words. Somebody stole my patty paper. So I'll use an old sheet. So I'm taking these coordinates I'm reflecting them, just like we do for an inverse, across the line y equals x. I'm reflecting them diagonally. And so I end up with angles on my x-axis, sine values on my y-axis, with -1 here, +1 there. Okay. And where I had 360 on the right, now I'm going to have 360 at the top, right there. Okay. So my axes get reflected. Settle down. We're all excited about sine inverse too. So let's try to keep it under wraps. Okay. So let's sketch a real quick graph of the sine function. Okay, it looks like that. So how would I figure out what the sine inverse graph looks like? So I can try and do the reflection in my head, and maybe we can get an idea. But let's take some actual points so that we see the mechanics of this. And so if I take a point from the original sine graph, like 0, 0, that's a point on sine of x. How would I find a corresponding point on sine inverse? So what happens between a function and its inverse with the coordinates? Yeah, they switch, which this isn't a great example of. But if I switch 0 and 0, I still have the point 0, 0. So that's going to be a point on my inverse. Let's do this with a few more points. What about the point 91? That's a point on the sine graph. So what would the corresponding point be on the sine inverse graph? Yeah, 190. So let's find that point. So 1 in the x direction and 90 degrees. Would that be up or down? Yeah, it's going to be up because it's positive. A positive y value. So there's the point 190, like that. So let's keep going. I'm going to stop writing them down. I'm just going to point. So this is 180, 0. Flip those. 0, 180. Here's 270, -1. Switch those. That's -1, 270. And I can start to see that sideways wave that Austin talked about a second ago. Here's 360, 0. Going to switch those. 0, 360. So what does it look like? It still looks like a wave. It's just reflected across this line y equals x. And I can continue this pattern out. So here's -90, -1. That's going to be -1, -90. So let's go ahead and finish this wave. Then -180, 0, 0, -180. -270, 1, 1, -270. And -360, 0, 0, -360. Okay, so real quickly, what I'm looking for here, how this graph is going to help me. If I want to know what angle has a sine value of the square root of 2 over 2, all right, watch for just a second. I'll find the square root of 2 over 2 here, which is about 0.7. And then I just need to draw a vertical line, and I have all of my angles right there, all these intersections. So that angle, and that angle, and that angle, and that angle.
I thought that could be a function of the
It's not a function, and if we had like 5 more minutes, we'd talk about that.
Okay.
We'll continue that way now.
Why'd you have soap around your neck?
I know. You want to save lives, or just keep people alive.
So you avoid cooking. How you keep them alive? You avoid cooking.
I make them happy by talking to them. Oh, let me tell you what happened last night.
Lord.
Oh my god. This person, I even told my parents, and they were like, oh, that's how they used to classify slaves. Because there was this one,
Oh, 'cause they're old.
there was one old guy.